Hello, everybody. Welcome to the first advanced lecture.
You're kind of skipping over some stuff.
All right, so we're gonna get started now. Right. So, welcome to the first advanced lecture of RUCP for this year or semester. So, okay, yeah. So today's lecture will be on segment trees, and we'll basically give you an overview of how the data structure works. We'll go over the template a little bit, and then at the end we're gonna look at a couple problems on how to use it. Just to note that this is going to be like a part one lecture on segment trees. We're gonna do some more things later down the line, but for now we're just gonna look at the basics. So let's get to the next slide. So here we should begin with the motivation of segment trees. And that is basically, we want a data structure that can support two types of queries or operations on an array of size n. And the first type of operation is we want to be able to update any element at any index that we specify in the array. And the next is to, if we provide it some interval, so a contiguous interval in the array, we want to be able to or give the some kind of the query answer for some function that we would describe. So yeah, so we'll get to that. And so for example, you can do we want to be able to process some queries on intervals in an array in log n time. So we want this to be efficient. Just a note on the log n. If you were to try this with, say, prefix sums, you would be able to do the querying very quickly, right, in constant time. But you would see that the problem is with updating, since whenever you update an element in your array, you would have to then recompute your entire prefix sum, which is then linear, and that's not what we want in this problem or in this setup. So we will now go to the next slide. Restate it a little more formally. We want exactly two different functions, right? The first is an update query. If we give it an index, we want to update that index to some specified value k. And then the other one is sum, or it can be other functions, we'll see later, but we want to, if we call sum, it will be given two indices. It will be a left and right index, right? Uniquely describing a subinterval of the array, and we want to then call the function on the entire, or compute what that subinterval would evaluate to. And we, again, just to rephrase again, we want this in log time. So, the answer, or the general approach to solving this, is to use a segment tree. And this is a data structure, which when you look at it, it's basically a binary tree, which will represent, where each node will represent the function computed on an interval, and the structure of the binary tree is quite important in that. So the root of our binary tree is going to represent the entire array, and then since it's a binary tree, each node will have two children, a left and right child, and those children will represent the left and right halves of that original interval. So so on the next slide here, we have the visualization of it. If we have that given array, 2, 4, 6, 1, 3, 5, 2, we would have at the root the entire array if we were doing the sum, right? So our root is now 23. And then on the left node, we would have the elements from index 0 to index 3. That would then give us a sum of 13, similar on the right. And we would keep going down until we get to the leaves, which are basically, one element, or each leaf would be, one element on its own. And a note about this is that for space complexity, we would basically need 2n nodes in our binary tree, because so at the bottommost layer, the nodes representing exactly one element, we'll have n of those. Then in the next layer, right, those will represent basically intervals of size like 2, but they will be disjoint. So that will give us n over 2 more nodes, then n over 4, n over 8, and so on. down to 1, and that will sum up to 2n. That's a, I guess, classic or mathematical identity, but that is the approach that we will try to use for this motivating problem. Now,
Oh, I guess.
good. Good luck. Okay, yeah. So if you have taken data structures, then this you will probably recognize this as the typical implementation of a binary tree if you were just to use a single array. So the idea is that you root it at the first index, and then for each index, you are able to basically assign it like implicitly 2 children, and those will be 2 times the index value and then 2 times the index value plus 1. And if you were kind of like trace it out, I guess on paper yourself, you would see that it would basically fill it in, or it would work out. And since each index would have a unique parent, and then again 2 unique children, and then we can also determine which one is the left and which one is the right from that. And we will, because we will have 2n nodes, we will have 4n memory because that's the worst case basically if we need to have a little memory at the end to account for some more children of our nodes.
Sorry, could you clarify that? How is it we have 2n nodes but 4n?
Yeah, so it's 2n nodes, but the first n nodes will have the children already like accounted for with the n like leaf, or not leaf, yeah, the leaf nodes. So the leaf nodes will only have n leaf nodes, since that's n over 2, sorry. Yeah, so that'll be n out of the 2n total nodes. So we'll have n that aren't leaves, n that are leaves, and then we'll need 2n for children of leaves that will remain unused. And that's how we get 4n. Yeah, the children that will be unused, basically.
So like if we had 16 nodes, we would have 32 places to have, or even more.
So 16 nodes would be for an array of size 8, right? So an array of size 8, would have then, our binary tree would have 16 nodes. The 16 nodes we would have in this set tree array. The first 8 would account for the ones that aren't of size length 1, and the last 8, which are kind of like the leaves on the tree, would be elements by themselves, and then that each of those would have 2 children, but we won't use those children, but we still have to give it space so that it won't break.
I have a question.
Yeah.
Why is the root node index 1?
Because if we make it 0, 2 times 0 is 0, so it gives us the 1 is just easier.
Is it like actually the index in the array, or is it like something?
Yeah.
The actual index of the array. Right?
Yeah. So I don't know. I think, did you hear that, Ken Thomas? Like, is Thomas like audible?
Yeah, I can hear you.
Okay. All right, yeah. So we don't have 0 because 0 would then point to itself, and that's problematic. So we just make it convenient and start at 1. All right. So moving on. So here is a visualization of how we would actually.
Who knows?
Okay. All right. So here's the example of how we would query the interval 1 to 3. So basically, we start at the root node, and we then consider the 2 children, and basically we can determine whether there's an intersection, right, with that and the target query that we have, because they're all contiguous, right? That's kind of the fact that we're going to leverage, so we can easily check that. So in this example, we see that 4, 6 does not contain it or intersect with it at all, so we just discard this entire part of the tree. So we move on to the left. Then, similar process. We see that 2, 3 contains it, and on the left we'll recursively, or I guess we'll iteratively in practice, go down further all the way to the bottom. Right? We see that 0 is not in it, and then we have 1, 2, 3 as the, or rather 1 and then 2, 3 as the 2 nodes which correspond to this query interval. So does that make sense? Okay. So on the next slide, we will see the pseudocode. So the pseudocode isn't very important for now. You can read it, I guess, but we'll actually look at the template a bit later. So it isn't too important, but it's basically what I just described. So we'll move on.
Yeah.
Okay, and then the other operation which we want to be able to handle is updating our segment tree. And so the process on how we would do that is we would begin at the root node, and we would basically traverse down the tree and end up at the leaf which we are updating. And basically, you may notice that our seg tree, since it's a binary tree, it will only have log n with levels, right? It will only have log n layers, or depth log n. And because of that, when we update each of these nodes, we'll only have log n nodes to update. That's because in this example, right, if we're updating the index 4, index 4 will only be contained in 4 of those nodes. So that is updating the segment tree. More pseudocode, we'll just move on from this for now, because it's basically what I just described. So we now are going to get into the actual implementation. So I think the template was next. So here's the general overview of the seg tree template. So some people use a struct like we have on the slides. Others like to use a namespace. So like the standard one, it's like a custom one for seg tree. But the actual specifics don't really matter because the template will have pretty much the same structure. So the whole power of the seg tree is that, or the whole point of having this template look like this is that it's designed to be very efficient at implementing yourself. So, or rather making it coincide with the problem that you're solving. So there will be only 2 parts to this, maybe 3 occasionally, that you ever really need to change. The first, which is actually the unimportant one, is n at the top, right? That's the max size of our seg tree. That you will maybe sometimes need to change if it's not conventional, maybe a little larger than normal, but you can usually just set that to be decently large and then not worry about it. So then the 2 parts which you actually need to worry about are first the identity. So TID over there, or you can basically think of it as long ID. And the other one is this function f. So the function f is basically the function that we're using in computing our queries on the array. So for example, we have addition, that's a common one. Other common ones are like min, max, some like rarer ones are like GCD and like LCM, I guess, and
Multiplication.
yeah, multiplication, I guess, but probably, yeah, that would be, or not many problems will do that because of overflow and stuff, right? So maybe mods, but will handle that, but yeah. And then basically the main rules which you need to have your function satisfy are associativity, like this. So we will explain that later. And basically, yeah, and once you have those 2 pieces, right, I didn't describe ID yet. ID is is a fixed value, right, that you set. And basically, it is the identity relative to your function f. So for example, if you're adding, right, the identity will be 0 because anything plus 0 is anything that you started with. The identity for, say, mins, if you're doing like the min queries, then that would be a very large number because you're taking the min of then a very large number and something is something, right? Then maxes is 0 if you're doing the positives, right? So ID is the value which wouldn't affect your query if you were to use it. Yeah, so that is the structure of this. Taking a closer look at the actual operation or functions that we have here. So our first one is modify. Modify is the update query. So yeah, we give it 2 values, or parameters. The first one is p, which is the position. It is the index, right, that we are updating. The second is the v, which is the value. And that's pretty much all there is to it. It will handle it for you. So a nice thing with this is that you can kind of treat it as a black box. So once you have a seg tree, right, or once you have the template, you can kind of just use it. You don't have to worry too much about like the inner workings, since it's kind of or since the intent of these templates is that they're
Wait, is T the seg tree here in the mod?
uh,
Or
small
what,
t.
what's yeah, small t. What's small t?
Small t is
small t
the array of
Yeah.
those. Yeah.
Yeah, so pretty much, yeah. Big T is
Oh,
a type. It's like
Type
long,
is
long. Yeah, so by default it's long, long. There are rare situations in which you would change that, but yeah, we don't need to worry about that for now.
wait, is this kind of like implemented like a heap, where like the array is like
Yeah.
Yes,
okay,
that is.
except you have the order enforced on the left and right still.
Yes. Yes. Yeah. Okay.
Okay.
That is the modify operation. Next, we have the build operation, which we don't use.
It just call and modify and times
Yeah.
array. Just change like each element individually instead of calling.
Yeah. So this is also true if you're going from test case to test case in your problems or whatever. Basically, if you want to kind of reset your seg tree, all you need to do is basically update each element or each index, right, that you will be using. And as long as you don't query outside of those indices, then your seg tree will work perfectly, right? Since you're updating it by nature of construction or by the construction of the seg tree, right, with the modified function, build is pretty much unnecessary. And then finally, we have the query operation. Like I said before, it does this. So we do it iteratively here. And the biggest thing to note here is that the query, so we give it a left and right value, right, for the query. The left one is inclusive, the right one's exclusive. So that is just easier to implement for the template, pretty much. That's the query operation, and and then you just like use it. You don't really need to worry about how it works internally. And then this is the full template altogether. And then the comments are there normally, or people tend to not comment too much when they do competitive programming, right? But in the templates, it's a good reminder. So yeah, all like the type of stuff that you need to worry about is not obvious, but it's labeled. It's labeled.
I know you had mentioned we should be using the build, and it's not even listed here. But with build, is that like you give it an array and it'll build from there?
Build.
Build will build it in linear time, right?
Yeah.
Call modify n times.
Well, okay, so it would be n log n, yeah.
Yeah.
So okay, so build I think would basically just fill the entire thing with the identity, but then you also want to.
Well, it just builds it bottom up.
So it'll be n log n
Or like
probably.
or however many
But
builds there are.
yeah, but since we don't use build, we don't need to worry about it. So
To comment on the chat, I want to just use C++, and then you said some form of element, I can't read it. For this template, you don't have to worry about like in competitive programming we use very bad variable naming. It's like pretty garbage. The main important thing to know is ID and F, which will explain later. You don't have to modify this for now, and then the modify and query, those are just pretty straightforward names. Yeah. You don't have to worry about like all the code here inside of the function.
yeah.
The shorter your names, the faster it runs.
And then I think one more thing. If you haven't seen LL before, basically it just means long. It's a little trick that people put at the beginning of their template. It's basically so in practice it just allows you to type LL instead of long, and that's enough for now writing long.
And you change it to T so that you can.
Yeah, why do we change it to T?
Yeah, so up there it is made T because there are some situations which we don't need to worry about where you wouldn't want long, but yeah, again, don't worry about that for now.
Oh, okay.
Like it decently long. Okay. So we'll now move on to sample problems, and the first one. All right, you by Thomas.
Sorry, this is kind of bad playing. I'm gonna have to go over just one small concept before we get into this. So the F function, you can change it. Basically, okay. The big hint is you're gonna need to change the F function. You're gonna change it to min, I believe. It's either min or max. It's one of the two. So What? So what you can do is just query the min across a segment. So that's just the big hint for this. Anyways, longest increasing subsequence, given an array of n integers, return the length of its longest increasing subsequence of O of n log n. And the constraints are n is less than 10 to the 5. AI, the key thing is AI is also less than 10 to the 5. Hey, that's just another hint. So for example, here, the longest increasing subsequence would be, right? Yeah. Can you guys see my mouse?
Yeah.
Okay. The longest increasing subsequence would be 1, 2, 5, 7, 8. You can also pick this 7, doesn't matter. Is the problem clear, I guess? Okay.
Increasing or strictly increasing? Or
Strictly increasing, yeah. Because otherwise we could have picked the 7.
Okay.
Yeah.
Wait, so instead of constructing it using sums, you want us to use min to
Either
get.
min, yeah, either min or max. I forgot which one is which, but it's one of those two.
Does min somehow give you the number of like the number of increasing like if all right, hold on, I need to think more about this.
Instead of A plus B, just do min A.
Yeah.
Min AB, yeah. So you take
Yeah.
the range instead of the
And
sum,
then
yeah.
and then your seg tree now is able to give you min queries instead of sum queries.
Oh, sorry, you take the max. No, this problem's definitely max. Sorry, you take the max, yeah.
Okay.
I've seen the solution without the secretary.
You want to get the n squared or binary search?
The n log n, but
Oh, don't say it. Maybe it can.
Maybe say it.
Sure, you
I'll
wanna-
save it for later. I'll try to think of the
Okay, yeah.
secretary one.
If you guys have seen this problem, and there's an O of n squared solution that's pretty standard using dynamic programming, and that can lead either to binary search or the secretary solution. So that might be a hit. I don't know how familiar you guys are with. Anything.
How much time we got?
Give it a minute or two, I guess. Any ideas, Michael?
Like think about it a little bit.
Okay.
Just like try out some ideas maybe.
That's some idea. So,
So like if you go like 1, 4, 7, 8, but that would only be 4. Max 1.
yeah, you want to pick the
Like
maximum.
order in
I think it could actually still take 4, because you want 4, you just switch with the 2.
That's true.
1, 4, 5, 7. Yeah.
Oh, 1, 4, 5, yeah,
7,
yeah.
There you go.
So it's maybe like a little hint because of that, right? Is that our approach would hit on the 1, 2, 5, 7 one, right? Not the 1, 4.
Oh, this is just the answer.
Wait.
Okay.
yeah.
Wait. What? Oh, this is okay. It doesn't even go into end square. It's just straight up solution. Okay, sure. So
Do you skip a slide?
okay, I guess here. Let me just do
Let's do that first.
let me do the end squared first. Is there?
Yeah, this is the solution slide. We get
Yeah, there's no intermediate slides. So I want to write on a whiteboard, but the people online can't see it.
Is it
Yeah, I mean, like the camera's looking there.
Okay, I mean, maybe just pull this off here.
Yeah. Can you turn? Yeah. Can you turn the screen to
Are you not sharing?
the board?
No, I'm sharing my. No, yeah, you guys can see. Oh yeah, change the presentation to this guy. Let me.
Oh yeah. You can share the screen. And, wait, it's Google Meet.
Wait. I can present your entire screen, your window. Okay, I'll just do an MS Paint, whatever. Okay, the idea, or I can even just use the mouse. Okay. So the idea would be, do MS Paint over here.
There's Aggie.io.
There is Aggie.io, yep. Aggie.io.
Aggie
Gone. Among Us House.
No, he was always using Aggie.io.
Oh wait, is this sharing the?
Oh,
probably
it's not
share.
sharing. It's not
probably
sharing.
not
Right.
sharing,
Good point. Good point.
Well,
Thanks.
You just have to share that.
Stop sharing that. You share the. Okay. So for the example, what was the example? It was
1, 4, 2, 5, 7, 3, 7, 8.
go with it.
1, 4, 2, 5, 7, 3, 7, 8. 1, 4, 2.
Windows key shift S to screenshot the.
Oh my god, I can't find the magnifying. This is insane. I know, it's just through Windows. It's not there. What? Oh, what the hell? Okay. So what was the example?
4, 2, 5, 7,
1, 4, 2,
5, 7, 8.
5,
7.
7. I'm just gonna do
Something 7, 8.
1, 8. Okay. So the idea is you want to see. Okay, we can always put one. We can always put the first index into the array because a subsequence of 1 is always increasing. Length of 1 is always increasing. Then 4, we want to look at what is the longest subsequence for this index 4, before this index 2, that such that 4 is greater than the subsequence ending in that. So here it'd be 1, so you can add this. You're going to make this a subsequence of like 2. Just store these counts in an array or something. 2, you can't like use 4 as a subsequence, so you can't like build off the chain of that. You can only use 1 as a subsequence. So this count would also be 2. And then you just keep on building it. 5, you can build out 4, so 3. 7, you can build out 5. This would be 4. And you would just iterate backwards, and since you're iterating 1 times, 2 times, 3 times, that's the sum of numbers from 1 to n, so that's roughly n squared in terms of time complexity. So that's the n squared solution. Yeah. Does that make sense to everybody?
Yeah.
Yeah. Okay. So the trick is here. Let me stop sharing this. Let me go back to the slides.
Oh, there's 2 here.
There's 2 different. They're not sharing there. So the trick here is you maintain a seg tree such that every index is the longest increasing subsequence with value with aj equals I. So like at index, let's say 1, and in that example, we put 1 in first. So we would initialize that to 1 initially, and then it was 4, right? So then 4 would query all numbers between 1 and 3. And that would give you, there's just an example here, yeah. Okay, so here you do a max query between 0 because 1 is only greater than 0. So you put 1 there, and then 2, 4. So notice here how you're querying all the numbers between 0 and 3 for the maximum longest increasing subsequence, because that's like the longest increasing subsequence of the numbers you've put so far. And then you would just add 1 to it because you can add 4 to that number. And then for 2, see how you're going back, you don't get the option of adding like 2 to itself, for example. So you would just put 2, you just put 2 there. Then for another 4, now you query between 0 and 3 again. And since there's a longest increasing subsequence of 2, you're basically just doing the backwards tracking, but you're doing it faster because you store the LIS array. And then max query, you query all numbers between 0 and 6 for all the subsequences ending between 0 and 6, and the longest one is ending in 4. So you just add 1 to that, put that in 7. Then you have a longest increasing, just same thing. Oh, I went a little fast. Same thing. 0 to 5 because. Oh, and by the way, the way we're getting these queries is every number from between 0 and that number we're trying to fix minus 1, because you can always add a number n to, and number n is always greater than every number from between 0 and 9 minus.
Wait, sorry, could you explain again where these query sizes are coming from? I didn't really
know. Okay, sure. So what the seg tree represents is the longest at each index is the longest subsequence length ending with that index specifically.
So you can't do this if like your range is from like negative trillion to trillion.
You can do this. There's like a technique called coordinate compressing where you just make all the numbers
Oh, okay.
between like 0 and n. But yeah, the general concept is it's a lot harder to do if you don't have like, as you said, the range of one numbers is large, and that's why the AIs between 10 to the 5 is a key thing to use here.
Oh, okay.
Yeah.
Wait, so these indexes 0 to 8, are they coming from the actual elements in the array? Like the fact that we have a 1 and 7?
Yeah, pretty much. Although you could just initialize a set tree to be large enough to have everything and ignore everything past your highest number implicitly because you never query beyond that. Yeah. And then you just speed up the thing with that. Does that make sense? I went a little bit fast.
So you start at 1.
Yep.
And then so you query for things that are 0.
Yep, and
there's nothing at 0.
there's nothing 0,
It's usually
so
1.
yep.
And then you go to 4, and you query from 0 to 3 because it's everything less than 4.
Yep.
And then okay.
Yeah.
I got it.
Oh, wait, so the queries are following the elements in the array.
Yeah, queries are
Yeah.
fun. Yeah, that's
So it's basically the longest increasing subsequence ending with that number.
That's the same idea in the other.
with binary search.
Wait, yeah.
Oh yeah, because they're just binaries. You don't explicitly keep every track of every
Hold
number.
on. Never mind, that's not true.
Not fully true.
It's not true. Binary search, you can make it so that the sizes of the numbers can be true.
Oh, but yeah,
True.
because it's just comparison.
Yes.
Yeah.
Yeah, okay.
But that's the same.
If you're like
intuition.
leveraging the fact, maybe, if you're like leveraging the fact that there's a pretty small bound on the actual elements of the array itself.
Guess does that make sense? Everyone in the chat, sorry. O(n squared. Yeah, Swapneo posted a good O(n squared solution detail in the chat.
Wait a second. I actually like how does the max sec tree max the sec tree using the max function, how does that give us the number of what is that giving us?
That's
when you
giving
query?
us.
Oh, does this actually? This just gets you the length of the.
Yeah.
Not what the actual subsequence is.
You can recover.
You have to like
You can
backtrack.
You can recover it by backtracking. Yeah. You like store a pair of things and then
Parents.
yeah. Sorry. I should. Yeah. Okay. So the max. Why we do a max query is because we're trying to find, because all the values in the array is like the maximum subsequence you found thus far. So then once you do the max query, you find, because you can only append to numbers that are less than you, so you just query all the numbers less than you, and you can each find which one is the best to append to.
Are you updating the sec tree at each step that you're iterating through this?
See how
array?
4 changes to 3 in this iteration.
If it improves.
The LIS array is the sec tree?
The LIS array is the sec tree. Yeah, exactly.
Okay. Well, okay. Got it. Sorry. Got you now.
So I'm gonna ask, what happens if you have duplicates in this approach? I believe it still works if you have duplicates.
Duplicate numbers.
Oh wait. Oh, do you mean like duplicates as in like duplicate numbers or like duplicates as in less than or equal to, like not strictly increasing subsequence? A duplicate elements in the original array. Yeah. So here it works even if you have like 4, 4, 4, 7. Yeah. So it works if you have multiple elements in the array. And that's because if you go through it left to right, I guess the intuition is that like you won't, it'll only care about the elements less than it, so they won't interfere with each other.
Even if there wasn't like, even if you weren't, we still like, instead of finding the max of our query minus 1, the max until it.
I'm pretty sure, yeah, you can do that. Yeah.
Or you could go backwards and look for strictly decreasing.
strictly decreasing.
Yeah.
I mean, just times everything with -1.
Yeah.
Yeah.
So.
Wait, but there's this operation of adding 1, like that happens,
oh,
right?
You can just
You can
Yeah.
think of it as basically finding an element that would increase the length of the longest increasing subsequence that would then end with that. So it's making like a longer, since you're appending it to the end of the longest one we've seen so far, that would be valid to add this to the end. The action of adding it to the end is the +1.
That doesn't necessarily have to
But-
increase on every time, right?
No, yeah, so that's why you have to make sure that you're only doing the max of
Yeah.
that and what you currently have.
Yeah.
Oh, wait a second. Okay, so I guess there's an implementation of this later on, where
yeah.
we'll see where it is.
Probably against the local marker. Yeah. Oh. Not implementation. Did I delete it? Oh my god. Okay. So. Okay.
Write it now.
Yeah, let's do it
Right
right
now.
now.
Right now.
Quick.
Right.
Oh,
yeah.
Just open up Notepad.
Okay. We'll show at the end of the thing. Yeah, the idea is, as Daniel said, you take the max between the query +1 and the current element. So you make sure you're not replacing with something worse.
The set tree contains the longest subsequent element with emphasis values, then check the next element, you get the longest subsequence, which emphasis values fall with the current one, which is like X. Then you can add.
Yeah, and as Swapfield said, yeah, that's that you do that, or you take the max between that choice and the currently already longest increasing subsequent. Yeah.
So why might you use this algorithm over the other LIS algorithm?
Because this one requires it to be bounded.
So that means it's just worse? Or like it's better in some ways?
I think you could argue with it should be.
This is I feel like it's more intuitive.
Right,
I don't know.
implementation.
For me, at
yeah,
least.
like
Okay, fair enough.
yeah.
What's the other LX?
We'll come back to this.
Okay, yeah, I'll go right there. Yeah. So in the secretary template, we noticed instead of just having like LL as our type and instead of just putting like adds everywhere, we have a function. We type def it to be some kind of type, and we have the function to be customizable. And this is because in some problems you can change. Even the previous problem, we didn't just use plus, we used max. So what the properties of changing up the f and t variables and IDIS is that f has to be associative. So what this roughly means is it doesn't matter which order. If you have 3 elements, if you combine the first 2 elements, or first and second elements, and if you combine the second and third elements, and then you combine the remaining 2, it doesn't matter. It doesn't matter which order you combine the elements in. And yeah, so also identity makes your life so much easier because just having dummy indices where it doesn't matter which it doesn't matter what's in there, because identity just means that no matter what, that identity, as Daniel said, identity plus X, identity F combined with X, it just returns X. So it doesn't affect X. Yeah. In math, this is called a semigroup. Just fun fact. And examples is addition and multiplication. Addition because you can adding 2 numbers is associative, and the 0 element is identity. Multiplication because multiplying 2 numbers is associative. 1 is identity. GCD, same thing. You can apply GCD as much as you want in any order. It doesn't matter. Matrix multiplication is the interesting one because it's unlike the others, which is commutative. Matrix multiplication is strictly associative, so that's why we have. So that's like a interesting implementation detail, I guess. And we'll see this actually really soon. Binary or and number numbers and some other crazy functions. Yeah. Does this make sense? I guess. Where you can swap out stuff and put different functions on the different objects. Okay. Okay. So now we have addition robot. Given string A and given a string consisting of A's and B's of size n, you have to perform two operations in log n time. The first one is updating a character at a position in the string to A or B. It just swaps to the other one. And the second one is querying like a substring from A to B, and then you do this following algorithm. You go through that substring. If S of I equals A plus equals B, else B plus equals A. And then you want to print A and B at the end of this process.
What does that mean, A plus equals B?
A and B are two integers.
Oh.
Yeah. And then you just do the repeated addition.
Wait, so we have, like, is there some intuition for what A and B is supposed to mean, like what they represent?
A and B are just any integer. Like they'll give you 4 integers, and A and B are
Is A and B between L and R? Is that what's going on, or is that like is it related at all, or what's L and R?
They're just like two numbers that they give you.
Is it a string of integers? Like if it's multiple digits, like can you like accidentally get another digit? Or is it an array of it?
Okay, so oh fuck, you pictures. Do you want me to go Aggie again? All right.
Like you have the string of A and B, but also you have them as integers.
Yeah, so you have this.
Oh.
Yeah, you have a string of A and B.
And then they tell you what they mean.
They tell you what. Yeah, so like you. They just imagine a string of A and B's. Yeah, and then you do some operations with them, and then the query part, you take a substring, and then you go through from left to right. If you see an A character, do the A plus equals B, else B plus equals A.
Oh, so this is something that we shouldn't think too much about.
This is some process, yeah, you have to like figure out how to do, yeah.
You want to be able to do the second operation in log n?
Yeah, the second operation on log n.
What? Okay.
Wait, what are the two operations?
Yeah, so S of I, it just swaps the character from
Okay.
a position I from the one to the other. So yeah. And then the second operation is you do the query, and then in that substring from L to R, you do the operation. Yeah.
Wait, if S of I is equal to A, so does that mean for every other character that's not A, we wait, else?
It's A, you add B, if it's B, you add A.
Yeah. And you store the
Oh, okay, hold on. It's because the string is only A and B. Okay.
Yeah.
Okay.
And then you want to print A and B at the end of this process.
And for the same entry.
Yeah. This is a hint. You're gonna have to use a different. You're gonna have to use a different data type than long ones.
Wait, when you add B to A or A to B, right? Is it possible you just get a third character that's neither A or B?
No, the character is the string is only ever A's and B's.
Okay, so it's like ones and zeros, addition mod 2, kind of.
Yeah. Wait.
No, I think.
Sorry. Yeah, the A's and B's. Are you talking about the A's and B's that they give you in the query?
I mean, like this string is of A and B's, right? And when you do the second operation, like let's say you're hitting an A,
yeah,
right? And you add B to the A, can the A become like a different letter from B or A?
A's and your A's and B's are like a separate variable. Like think about it as like X and Y for the V of L, comma R, comma X, comma Y. So as I equals
can we have a concrete example of the operation? Maybe that would.
that would be okay. So here for the string S of ABB, you have A equals 1. Let's just say start with A equals 1, B equals 1. Then because you hit character A first, you add B to A, so 1 plus 1. Then you hit B twice, so you add 2 twice. Once to B and once 2 to B again.
And I think the queries, the A and B that we get could be arbitrary.
The A and B's can be arbitrary, yeah. This is all, you don't have to worry about overflow. This is all under mod. So,
Oh, okay,
Yeah.
I think I.
Yeah?
Oh, yeah.
you wanna share a solution?
Wait, let me,
Okay.
let me like put it into words.
Alright.
I mean, so like. Guys, stop looking at me.
Wait, what's wrong with like just doing it? You know what I mean? Like,
Because the A's and B's, they can be like, because you simulate the whole entire process is it takes O of n. So you have to do it in,
oh, is n too big?
n is too big,
I-
yeah.
Okay.
You do it
I didn't see the
Yeah.
the constraint.
10 to the 5, yeah. Yeah. Do you want to share? We're probably gonna.
I think you can make the operation in your seg tree like, I don't even know what to call that, but like an A-B thing, like when you see an A, you have.
It's it's kind of there. There's you can. Is there maybe your thing? Okay. Okay. Yeah, it's matrix multiplication. So as you said,
What?
so you could store the protocol A plus B as matrices, and you can verify this if you just add if you if you multiply AB with this first matrix, you get A plus B and then B, and then this second matrix you can multiply that with this second matrix and B, you get A and A plus B. And
You don't need matrix multiplication to do that. You can kind of just hard code the behavior into your own function.
Yeah.
Oh, okay.
Yeah. But matrix multiplication is the intuition behind it, yeah.
So like the idea of the matrix multiplication, once you do it for a certain second, you kind of like done the computation and you can just plug in your values.
Exactly, yeah. And then you get basically just get the counts for everything. And you just, as you said, just plug in the values. And then and swapping operations, you can just swap the matrices to do that. Because if you look at what? Oh, because actually not even sure what.
That's just.
Okay, that just happens if you brute force it apparently. Okay, and then in the implementation. Move on. Okay. At least there's ignore that part for today. But in the F function, you do 2 times 2 matrix multiplication, and the IDT, you do the identity matrix. So anything multiplied by 1, 0, 0, 1 is the same thing, and then the T is a matrix, 2 by 2 matrix, a pair of pairs. Yeah. Let's move on. Yeah.
So for the last problem for today,
This is easier.
yeah, so this one is integers have friends. That's the title of the problem. It is from Codeforce, so we'll cite it at the end. But basically, the setup of the problem is that you have an array of size n, and each integer is pretty large, 10 to the 18, so you can't exploit that really. Then the array is a standard length, so you can do n log n on it. And basically, you define a friend group to be a contiguous subarray such that all the elements in that friend group will satisfy having the same residue modulo some mod that's greater than or equal to 2, since 1 is trivial, right? That would not be interesting. So that is the set of the problem, and we want to find the largest friend group that would exist in this array. Yeah. So let everyone think on that for a little bit.
Are we given M or do we find?
You have to, yeah, if there exists an M. So you are not given M at all whatsoever. You're just given an array.
It's a range where, like, if you modded everything in the range, going 1, 2, 3, 4.
No, so everything in the range would have to have. So if it was like 1, 2, 3, 4. Actually, that's not a good example. Basically, a friend group, right, would be if you took some like contiguous subarray,
Yeah.
right, and then there would exist some modular value such that every element in that subarray would have the same residue if you took all those things mod
It's the
n.
same result.
Yeah, same
They're all
result. Yeah.
equal.
So for example, 2, 4, 8, 10 is a friend group because they're all 0 mod 2, right? So that is the setup of the problem. The first step I think we can give because, yeah, I think we. Oh, actually, yeah.
I don't know if this is right, but would you only do about prime
Okay,
M was
that is a good point. Yeah. So if you have anything that's not or anything that's composite, yeah, you can break it down to primes and get pretty much the same result. The only problem is that doesn't help you too much, unfortunately. But that is a true observation. Yeah.
Wait, is it because you can have non-zero residues that might
If
become?
it's composite and they all have the same residue, then they'll surely have the same residue mod factor of that mod of that
It's
modulus.
GCP.
Okay. So on to the next slide. So if you were to write this out, right? We kind of want to think about if we can determine whether or not a friend group or an array or subarray is a friend group using a seg tree, right? So we begin by kind of writing out if we're given AI through AJ, right? We would know that we can write this as some common residue plus some random integers, right? As the multiple multiplication factors to some common modulo m. So this is the setup. And then are there any like observations we can get from this?
What if you sum everything together on both sides? Is that not
Summing,
the right direction?
so not
Do you have
kind
to
of.
return M?
No, you don't care about m. You just want to find the size of the largest friend group. And summing, so the problem with summing is that then the length of the array will kind of give you like different results all over, right? So, because then you'll have r times the length, which can be then anything mod m, right? Depending on how long your array is.
Oh, okay. Yeah.
So that doesn't help too much.
Okay. I didn't like verify this, but if a subarray all has the same GCD, does that help you?
Okay, that's on the right track. So if we go to the next slide, instead of addition, we want to take differences. So basically, if you remember from before, whenever we take a difference, right? So in order for a subarray to satisfy those conditions, any difference would have to be divisible by n, since or between pairs in that subarray.
Okay, that makes
Because the residues cancel, right? And now you have the difference in the k's times m, right? So you know that. And then you can actually, and also absolute distance, so we're taking the absolute value. And then the fact that you can extract from this is that you can actually simplify it to just adjacent pairs because those are enough, right? Since if you have A and B, or AI and AI plus 1 belong in the same friend group with a fixed m, and then AI plus 1 and AI plus 2 are in the same work with the same m, then AI and AI plus 2 will again work with the same m.
Oh, so GCD, so you make a new array of the differences.
Yeah. So that's we want a seg tree of GCD, right? Instead of a seg tree of anything else. That is the function f that we want to change, right, in our template. And then I guess just to quickly note, the identity, right, for GCD is 0, not 1. 1 would not is not what you want. 0 because GCD of A and 0 is A, whereas the GCD of A and 1 is always 1. So we want a GCD seg tree, and now we want to think about how a GCD seg tree helps us.
Can you sliding window?
Oh, you're on the right track. So yeah, it's a general idea. It's like a general archetype. So on the next slide, which is the final solution, we want to think about what happens when we fix the left beginning index for our friend group. Now that's going to be I, right? We fix that for each one, so that's already a linear runtime, and we want to figure out how can we figure out the maximum possible ending or the right index, right? That gives us the longest possible friend group in sublinear time, right? And this is like a general strategy, right? And the way you would approach this is by using binary search on this array of differences, or rather absolute differences. So in this example, right, this is our original array. We make our array of differences, absolute differences there. And then the algorithm would basically iterate for every possible starting index. We would binary search the ending index. And we can binary search quickly because we can query our GCD seg tree to check if that GCD is greater than or equal to 2. Since that would imply that we have some m exists, right? If they all have the same, if the GCD, is greater than or equal to 2. And that will work in the binary search in practice, where if we see a 1, right, if the GCD is 1, that means we overreached. So we have to jump back in typical binary search fashion. So you can kind of imagine this array being pretty long, and then we'd have to binary search it as appropriate. Does this make sense?
Well, and then the runtime for that would be
it would be
log n times log n.
Times n, because we have to, so it will be log n times log n if we fix the first index, but we also need to fix the first index for each n, for each I, right? So that is n log n log n. Yeah, because the binary search is log n, and each check on the binary search requires a
GCD is also log n, so just be log one.
But isn't GCD already computed when you build the tree?
Yeah, but to query the tree, you go down the.
Yeah. The seg tree is already
The queries are log n.
constructed.
Wait, no, was I saying that right? Because you mentioned GCD is also log n.
Maybe.
Oh,
Maybe.
GCD operation itself.
Sure.
But I don't know. But I was thinking it's already pre-computed.
It's small enough to not worry about it. But the point is, it's a lot smaller than n squared. And it's not that much bigger than n log n. And that was integers have friends. Are there any questions on that? Doesn't look very good. Okay, so now we'll do the conclusion. Never mind. We have the implementation. So here is the implementation. I hope it's readable. It should follow like the general logic of what I was talking about before. We have the read in, modify, or set up the seg tree, binary search on it, take the max each time. Yeah. So that is integers have friends. And that's the implementation. So it looks like finally we have the conclusion. So thank you guys for coming. That was our first advanced lecture of the semester. And make sure to check out our resources, problems. Link to the folder will be on Discord. All this will be on Discord. And thank you guys for coming. And on the next slide we have the problems.
Oh yeah.
Or seg tree templates. If you want a seg tree template, I guess just use that, I suppose. You can also ask me if you want what I use. And finally at the end we have the problems. And that was the seg tree lecture. So thank you guys for coming. I hope you have a nice evening.